Yung sisnado sa babae, tatlong isang malaki, dalawang
All right. Good evening, everybody. Welcome to another session, another training from Ivan Learning. So my name is Tony Gabriel, and I'm with you again tonight. Hope everybody's doing well, and I hope that everybody can hear me. Okay. How are you guys doing tonight? We're glad that you're with us tonight and you're participating in this training. Welcome to another series of ACM, another session or another series from ACMV. Even Learning provides quality trainings and seminars conducted by your peers. For tonight, our training is overview for mechanical ventilation. And this training, you'll be able to determine what are the ventilated spaces, determine what are the ventilation requirements, and know what is air pressurization. As we go along in this training, you may have questions. Please feel free to write your comments on the comment section in Facebook, or you can do the chat box, use the chat box here in Zoom. We will get to them during our Q&A portion. And if you have questions unanswered or remain unanswered, please email us at evanlearning.sg@gmail.com. This training is approximately 1 hour, including the Q&A. So tonight, your instructor or your teacher for tonight is me. My name is Donnie Matthew Calpo Gabriel. I'm a professional mechanical engineer, and I have more than 20 years of experience in ACMV design and installation. Okay, let me share to you my screen. All right. I see that there are some more people joining us. Welcome again. Welcome again from Even Learning. So again, our topic for today is the ACMV series. This is part 1 of 5. So we're now doing the overview for mechanical ventilation calculation. For those of you who want to see the first part, overview of heat load calculation, you can do that. You can check our Facebook page, and the recording is there. Right. So overview of mechanical ventilation calculation. Again, my name is Tony Matthew Calpo Gabriel. I'm a PME. Oops, wait, let me get this thing straight first. Oops. I want to see if other people are joining in. Wait a while, give me a minute. Sorry about that. Sorry about the interruption. Let's do this again. Screen share. There you go. Again, there you go. Sorry about that. So for tonight, we will study 3 things. First, ventilation spaces. What are the ventilation spaces? Second, ventilation requirements. How are we going to know what are the ventilation requirements for each space? And last one is air pressurization or airflow control. First, ventilation. What is ventilation? Ventilation is the intentional introduction of outdoor air into a space. So this is intentional. So when you use mechanical equipment to introduce outdoor air into a space, that is called a ventilation. However, there are different types of ventilation. First is natural ventilation, where you don't need any mechanical equipment to introduce outdoor space. Air flows through naturally. Second is your mechanical ventilation, where you use fans or blowers to introduce outdoor air into a space. And there's also a mixed mode, where you take advantage of the natural ventilation and supplement it with mechanical ventilation. Since we are doing calculation for mechanical ventilation, we will not be tackling much about natural ventilation and mixed mode, but we will be focusing on mechanical ventilation. How are we going to size up your equipment? How are we going to know how much air needs to be put in or introduced into a space? Okay. Ventilation is mainly used for controlling indoor air quality, controlling the temperature, or other requirements specified by the space. So let's go first with the first. Requirements. Ventilation, because we need to control the indoor air quality. What is indoor air quality? Okay. So let's have this as an example. Example, there's a space. Let's call it as a wood shop. The floor area is about 30 square meter. Room height is about 3 meters. Okay. We need to introduce fresh outdoor air. Outdoor air is also sometimes called fresh air. So we're going to interchange that term quite frequently, outdoor air and fresh air. So in this wood shop, we need to introduce fresh air into a space. How much fresh air is needed? So there are two considerations. First, based on the space itself, so that the space will not be stuffy, we need a specified amount of fresh air to be introduced in the space so it won't be stuffy. Second consideration, the amount of fresh air based on occupancy. So based on how many people are going to be in that space, because they are breathing, the people will need fresh oxygen and will exhale out carbon dioxide. So we need to dilute or remove this carbon dioxide. So based on the number of people inside the space, we need to have a specific amount of fresh air. To be able to determine how much fresh air is needed to a space, we usually use ASHRAE standard 62.1 2019, or the ventilation for acceptable indoor air quality. Again, our example here is a wood shop. So going to table 6.1 of ASHRAE standard 62.1, we could see the wood shop here. There's two criteria, people outdoor and area outdoor. So people outdoor is based on the occupancy, and the area outdoor is based on the area of a space. Take note, this doesn't consider the height of the space. Just consider the horizontal floor area. So this on our example, we have a wood shop. So we see here, there's people here, people outdoor air rate. It says here 5 liters per second per person. So meaning if a person inside the wood shop, I would assume that he would be doing wood shop things or doing work, he would need about 5 liters per second of fresh air into that space. If it's just a space itself, the area needs about 0.9 liters per second per meter squared. This 20 here is the assumed density or occupant density, meaning for every 100 meters, there should be 20 people inside. So let's go back to our example. Our example is wood shop. The amount of air, M, needed inside the wood shop based on area is 30 square meter, our area, times 0.9 liters per second per meter squared. So we will get about 27 liters per second. But if we consider the occupancy, the amount of fresh air required is the occupancy times the ventilation rate. Our floor area of our wood shop is 30 square meter. Our density is about 20 person per 100 square meter. So you multiply that times 5 liters per second, we will get about 6 person having 6 liters per second, so about 30 liters per second. You compare the two based on our area requirements and our occupancy requirements. We choose which one is higher. So for this wood shop, we would be needing about 30 liters per second. So quite easy, no? Again, we use, we use a table 6.1 from ASHRAE standard 62.1, 2019. Based on this criteria given to us, we were able to calculate the amount of fresh air needed based on floor area and based on occupancy. There's one more method of calculation based on air change per hour, or ACH. So this method considers the volume or the floor area and the height of the space. So again, our example is wood shop. Floor area about 30 square meter, room height about 3 meters. So volume about 90 cubic meters. So based on Singapore Code 553/2016, or Code of Practice for Air Conditioning and Mechanical Ventilation for Buildings, wood shops or factories would require about 6 air change per hour, meaning the air inside the space must be replenished 6 times per hour. So what we do, we get the volume of the space, 30 square meter times 3 meter height, times 6 air changes per hour would give us 150 liters per second. So our previous calculation, if we consider ventilation space requirements, we would only need 27. If we consider occupancy requirements, we need 30. If we consider ACH, or air change per hour, we need about 150. So for us as a designer, as a person calculating this one, which value are we going to use? Of course, we would use the most high or highest value. In this case, the 150 liters per second. So we will use this one. Aside from our wood shop, there are also other areas that requires ventilation spaces. These areas are, I would say, specified by ASHRAE standard 62.1. Again, this one is table 6.2. Here, on this table, it will tell you the exhaust rate or the fresh air rate, exhaust rate, fresh rate, almost the same. And it will also give you air class. This air class we will discuss later. All right. Ventilation space, again, is mainly used for controlling the indoor air quality so that the occupancy inside will be able to breathe, or breathing zones, or the area will not be stuffy, and will not be stuffy by diluting and displacing the indoor pollutants. Indoor pollutants are sometimes the molds, or the molds that are growing there, or the foul odor. Earlier, we used 2 standards. First is the ASHRAE standard 62.1, 2019, ventilating for acceptable indoor air quality, and we use the SS553, or the 2016 Code of Practice for Air Conditioning and Mechanical Ventilation. So sometimes we would be confused which code or which standard are we going to use. However, local codes always supersedes the international codes. The international people will not be signing your plans, so the local people or the local authority will be the one signing your plans. So always follow which is higher based on the local codes. So if the international codes give you a higher value, of course the local codes will be able to be satisfied. However, if you are strictly doing your projects or your construction works, please be aware of your local codes. I'm based here in Singapore, so the references that I will be showing today will be based on the Singapore code, or SS553. But if you are placed in Philippines, or you're located in the Philippines, please make sure that you are well versed also in the Philippine Mechanical Engineering Code. So there are the numbers and the requirements are written there. Next, ventilation used for indoor air temperature. Okay. So again, let's have another example. Example, lift motor room. The lift motor room, inside the lift motor room, we would estimate or would assume that it has a 500 watt of heat load. Floor area, again, 30 square meter. Room height, about 3 meters. How are we going to know how much fresh air or how much outdoor air need to be introduced into this space so that it will be able to be acceptable? First, what are the requirements? What are the formula? Sorry. The formula is Q is equal to MCP delta T. Very familiar. Q is the heat gain, CP is the specific heat of air, M is the flow rate, air flow rate, and delta T is the temperature difference. So to get this, M is equal to 500 watts. 500 watts, this is the some assumed heat load, over CP, specific heat of air, 1 kilojoule per kilogram per degree Kelvin, times 40 minus 32. So this is where the tricky part is. Where did we get the 40 and where did we get the 32? 32 is the outdoor air condition. So here in Singapore, in the SS553, it is stated there that for every design of new buildings, the outdoor temperature is assumed to be 32 degrees Celsius. If I remember correctly, in the Philippines, it's 33 or 34. So please check on your local requirements or your local codes. What is the outdoor air condition? If code does not specify, please go and check your weather data. And then the other temperature here is the 40 degrees Celsius. What is the 40 degrees Celsius? 40 degrees Celsius is the acceptable ambient air for motors to run. However, please refer to your manufacturer. The 40 degree is assumed and common ambient temperature. So for example, our requirement earlier, this lift motor room requires at minimum to be at 40 degrees Celsius so that the motors can run. Your building manager or your facility managers may require you different temperature condition, but at the minimum, it should be at least 40 so that your motors will be able to run. So calculating these numbers, we will get 187.5 cubic meters per hour. Another one for thermal comfort. So earlier it's 40. Some people would say, oh, that's a bit too hot. So let's try a different one. Temperature requirements is 24 degrees Celsius. So our example now is a laboratory. Again, the assumed total heat load is about 500 watts. Floor area, 30 square meter. Room height, 2.5 meters. Humidity, 50%. SHR or sensible heat ratio, 100%. So we are not considering any latent heat here. We are only considering sensible heat. Okay, same formula. MCP delta T, 500 watts, 1 kilojoule per kilogram per degree Kelvin. This time, 24 minus 13. Where did we get the 24 and where did we get 13? 24 from our assumption earlier is the required room temperature. 13 is the dew point temperature of the area, 2450. So meaning at 2450, if you go with your psychrometrics, there you go. If you go with psychrometrics, at 2450, 13 is your dew point, which means this is the temperature of the air at 100% humidity. So 30, which means the coldest that you can bring inside here on this space would be 13 degrees Celsius. If you introduce air colder than 13, condensation will start. So if you introduce more than 13, no condensation, then it's okay. if you introduce more hotter or higher temperature, which means your total air will increase because you would have a smaller delta T. So in doing so, we assume at 24 degrees Celsius at 50% RH, relative humidity, we will be able to get 136.4 cubic meter per hour. Before I continue, is there any questions? If you have a question, you can unmute yourself and ask question. You're free to do so. At any time during the presentation, you can ask question. That's not an issue. It's not a problem. So you just unmute yourself and ask a question. All right. If there's no question, then I will continue. For the third one, ventilation for air motion. One of the energy law, energy in is equal to energy out. Why do we want to have air motion? To control pollutants, to control odor, and to control temperature. Okay. Example, this is a restaurant example. All right. Inside the restaurant, we will have air motion or flow of air going from one place to another. I marked here green arrow for fresh air and red arrow for exhaust air. First example. Here in the kitchen area, in the corner. Here. Kitchen area. Of course, because of kitchen area, there's foul odor or smell of smoke, smell of food being cooked. You don't want this odor to come outside and to your customers. So you would like all this air to be exhaust out and fresh air will come in. However, energy in is equal to energy out. Example, this kitchen is exhausting out 100 cubic meter per hour. It means this kitchen will also need total of 100 cubic meters per hour. So 90 will be introduced by fresh air. The other 10 will be coming in from your dining area. Another example is this toilet area. This toilet area example, there's 40 cubic meter per hour of air being exhaust out. You would also need to put in 40 cubic meters per hour of fresh air. So if you add up all these green arrows, 70 plus 90 is equal to 160. It should total to your exhaust air, 100 plus 10, 110, 120, 140, 160. Energy in is equal to energy out. You have to have your energy balance. So by doing this way, you can see the air flow or air motion inside your space. By controlling the amount of exhaust and fresh air coming through your space, you'll be able to estimate and predict where the air will be going. So example here in the kitchen, I'm exhausting out 100 and I'm putting in 90. So which means die or no choice, it will be coming from this side, from your dining area. If I'm exhausting out 40, so I'm putting in 70 minus here 60, so which means there's 20 cubic meters per hour left of air. Of course, it will come out from your doors. By having this energy balance, you'll be able to estimate where the air flow or the air direction will be going to. Again, we're at ASHRAE standard 62.1 2019, table 6.1. Again, earlier I mentioned about the air class. This air class tells you which air from what area can go to another. Okay. Our example here earlier is a restaurant. This kitchen is class 2, which means the air from here is class 2. Here in corridors or break rooms or coffee stations, which is here, these are class 1, which means air from here cannot go here, and air from here can go here. If you're from one class to another, so there's 4 classes, 1, 2, 3, and 4. Class 1 can go to class 2, class 3, class 4. Class 2 cannot go to class 1, but can't go to class 3 and class 4 spaces. Class 3 can go only at class 4 spaces, but cannot go in class 1 and class 2. Class 4 spaces cannot go to class 1, class 2, class 3. So there you go. By doing so, by this table, you'll be able to determine which air can go to which place. So in our example, this dining area is class 2, this kitchen is class 2. Sometimes as a cook, you want your food to be smelled by dining people so that they will feel hungry and they will feel excited to eat. So that's why the air is acceptable to interchange between the dining and the kitchen. But they cannot go to the bar area. So this bar area is class 1, this dining is class 2. The air from here cannot go to here, but they can go to here. All right? Question? No question? We'll continue. Sometimes the exhaust air and the fresh air, sometimes they're installed too near and would cause cross-contamination. Cross-contamination is when exhaust air or air from a lower class goes to a space of a higher class. Example, class 2 air goes to a class 1 space. That's cross-contamination. So how do you determine cross-contamination, or how do you avoid cross-contamination? You can avoid cross-contamination by referring to ASHRAE standard. Again, ASHRAE standard 62.1 2019, table 5.1. There you go. Minimum distances in feet. So which means, going back to our example, is class 2 going to class 1 area. So 100 cubic meters, the exhaust space for 100 cubic meter per hour into the intake space of a 70 cubic meter per hour. It says here on the table, class 2 air exhaust outlet must be at least 3 meters or 10 feet away from your fresh air intake. So on and so forth. For example here, garage entry or garbage area, dumpsters. So this garbage area must be at least 5 meters away from your fresh air intake. Else, there may be cross-contamination, or the smell from here go to here. For example, here, the smell of your toilet, you don't want to go inside your dining space. So your toilet should be more than 3 meters away from your fresh air intake. In our example, they're very far away. So that one is no worries. So this table 5.1, air intake minimum separation distances. This would give you a guide of your exhaust points. How far is it needed from your fresh air points? Again, another one. This one is a car park. So one shot of a car park here in Singapore, you would notice this exhaust points. Sometimes the code will provide you or will specify to you. In this case, this is not ASHRAE standard. This is 553, SS553. It would state there, exhaust part of a ventilation system must be at least 650 mm above the finished floor lines. So please note, this table tells you the distances between the fresh air and the exhaust points. However, sometimes the local code specifies where your fresh air and exhaust points are. Just one example is this car park. Car park, they would specify to you that at least 50% of your exhaust points must be at low level or 650 mm above finished floor line. So please take note on that. Please take note on your local code requirements. So that's it for control of indoor temperature using ventilation and air motion. So any question? No questions yet? I'll continue. Ventilation is also used for satisfaction with other requirements or indoor environments. Example, firefighting or life safety. Ventilation is used. This one is staircase pressurization. Ventilation is being used for staircase pressurization so that fire will not go to your escape route or your staircases. These calculations and these applications would require different sets of calculations and different sets of codes to be used. Another one is your smoke exhaust fans. Your smoke exhaust ventilation also requires a different set of codes and calculations to be used. So for this one, these are specialty calculations or specialists. So here in Singapore, we call them specialists. So they're mainly doing calculations for a specific application of ventilation. Our examples earlier is for normal uses of ventilation, included in air conditioning. So for specific application for mechanical ventilation, there are separate codes and separate procedures how to calculate them. And if you are interested, please drop me a line and we can share with you and discuss with you more thoroughly. Another example for uses of ventilation is to control the impurities. So here in our photo, our example is the kitchen hood. So different calculations again for kitchen hood to be able to size the hood and the location of the hood, to be able to capture all the fumes coming out from your kitchenware. So this one also requires different sets of calculations. Similarly, similar to kitchen hood are chemical storage. This is laboratory equipment or the fume hoods. These are called fume hoods. So this one is to ensure that the chemicals or the chemical fumes will not be contaminating the breathable space. Earlier, we have discussed the car park system. This car park requires, again, a different set of calculations. You would need ppm or the CO meters to be able to determine the required flow rates or required ventilation rates for car park systems. And these are chemical cabinets. These chemical cabinets also would require ventilation so that the chemical fumes or the chemicals will not mix with each other, avoiding any hazards or chemical reactions from each. In conclusion, the ventilation spaces we can see in our local code requirements or SS103 or international codes. We have used the ASHRAE 62.1. So this is the code for ventilation requirements and air pressurization or the airflow. So Just like we mentioned earlier, some cases, some applications are very specific, just like the staircase pressurization, where air pressurizations are also specified and calculated. If you want to learn more, please drop us a line and we can discuss with you in further details. Thank you. So, any question? Wala naman? No question? Thank you very much. If there's no question, this is the ACM. Oh, wait, we have a. There. This is the ACMV series, part 2, overview of mechanical ventilation calculation. The next part is part 3, overview of duct design. This will be for next week, December 19, same time here at Even Learning. For the next class link, it's on the Even Learning page. There's a registration. There's a registration form there, Google Forms. You could register there, and we will send you the link. So please register, and we'll send you the link for next week. For SS553 copy, it's a licensed copy. So I would encourage you to go to Spring, Singapore, and to get your copy there. So, any more questions?
Hello, sir. Good evening.
Yeah.
Sir, pwede po makakuha ng kopya niyo, sir, ng presentation since nalate ako, sir, kasi galing ako sa isang webinar din.
Walang problema, sir.
Thank you po, sir.
For this recording, it will be posted in Facebook. So you could rewatch them at Facebook. And for those who have registered, for those who have attended, I will be sending the presentation slides also after this session.
Okay, sir. Thank you po.
All right. So, any more questions?
Sir, meron ako.
Yes po. I would like to my dad. Yes. Yes po.
Kindly explain yung exfiltration at saka infiltration in terms of control of the fresh air requirement for air conditioning.
All right.
Dahil kasi yung fresh air or the ventilation requirement component kasi sa air conditioning presents some problems sa mga areas like magkakaroon niya ng pagpapawis ng maroon when these are not properly controlled.
All right. Thank you, Engineer Gabriel. Thank you po. Let me share my slide again. Give me a minute. All right. Share. So Engineer Gabriel gave us a very interesting and very nice question. No? There. Okay. Our example earlier for a restaurant. Engineer Gabriel introduced two words. So let's define first. First is infiltration, and the other one is exfiltration. So infiltration, by the word itself, infiltrate, so something that goes in. And exfiltrate or exfiltration is something that goes out. So for example, in our restaurant, our beautiful restaurant, assuming somebody on the patio here, oops, sorry, let me go through that again. All right, somebody inside on the patio eating, and he wants to go inside here, maybe here on the bar to get some drink. So when he opens the door, there are two things that's going to happen. One, air from outside will go in, or air from inside will go out. All right. So that's a two scenario. Air from outside going in is called infiltration, and air from outside going out, that's called exfiltration. Now, for like what Engineer Gabriel said, for air conditioning engineers, this is kind of a problem, because when you let air go out, you're basically wasting money or throwing away money. But when you let air come in, it will give you problems. Why? Because the outside air and the supply air of the area is too far apart, meaning condensation may happen. So when you keep introducing air from outside that's not treated, it will have contact with your supply air, which would be in low temperature. Condensation will appear. So sometimes this condensation will create damage to your property, like wall bleeding, or your wall is wet, introducing molds, or the paint will chip off, will damage your equipment and your furnitures and your walls. That. So to understand this, on our example, we introduce exfiltration. So air from here will be coming out. The amount of air coming out can be calculated. However, to calculate that, drop me a line so we can discuss with you how to properly calculate it. But for the time being, let's just say exfiltrate. For me, as I do my calculation and as I do my practice, I prefer to exfiltrate air more than to have the opportunity of air infiltration. I don't want the headache of calculating the infiltration, so I always oversize my equipment and exfiltrate air. Thank you, Engineer Gabriel. Thank you for your wonderful questions. Any more questions?
Hi, Engineer Tony. May I ask about? Can you explain a little bit on the positive and negative design of mechanical ventilation?
Okay. Magandang tanong po yan. That's a very good question, Engineer Tadina. So let me share my screen again on the same place. All right. Okay. So here, positive and negative. Engineer Tadina's question is the positive ventilation and negative ventilation. Example, this green arrow. Oops. This green arrow, this 70 cubic meter per hour. Let's say I did not put any fan here. Let's say I just put a wall opening here. And I put a fan here at the exhaust air. So here there's a fan, here there's a fan, here there's a fan. Meaning there's a fan here exhausting out 100 cubic meter per hour. There's no fan here. Because of this fan sucking out 100 cubic meter per second, this space becomes negative. Kasi hinahigop mo yung hangin eh. Dahil hinihigop mo yung hangin, the fan is sucking out air. Because you're sucking out air, the air is being sucked, the space where the air is being sucked out will have negative pressure. That's why that is called negative ventilation. But as the air is being sucked out here, I put a fan here. This fan will blow in 90 cubic meter per hour. Because I am blowing this fan, because I'm blowing in or introducing air to this space is still negative because the exhaust is higher than the out is higher than the in. So this space is negative. All right. This area, this dining area, I put a fan here. This dining area, if I put a fan going in, is a positive area or a positive ventilation because I'm introducing outdoor air to this space. So this space becomes positive. If this is positive and this is negative, the air from here naturally goes here. This is negative because if I put a fan here on the toilet, sucking out 20 cubic meter per hour, 2 fans. So this area becomes negative, this area becomes negative. Since this area is positive, this area is negative, the air will naturally go from positive area to the negative area. So this is how we do the positive and negative ventilation, controlling where the air, predicting and controlling the flow of air, where the air will go to. Nasagot ko po ba yung tanong ninyo, Engineer Tadina? Was I able to answer your question?
Yes. Yes, thank you.
Thank you very much. That was a wonderful question. So any more question? I have a question here from Gerardo. Sir, lahat po ba ng room space kailangan ng fresh air or some areas supply and return lang pwede na? All right. Earlier, let me share my screen again. Share screen. This one. Share. All right. Spaces is mentioned in 2 areas. First, table 6.2, meaning these usually are ventilated areas lang. So they are not, they need to have a negative space, or they need to have a negative air pressure. So this one, they have minimum exhaust rates. All right. Another one is your local codes. For us in Singapore, SS553, there are specified areas in which fresh air is required. Here in table 5, it says here, outdoor air supply ventilation, outdoor air supply for mechanical ventilation in non-air conditioned buildings or non-air conditioned spaces. So these areas, if they are non-air conditioned, then these are the ventilation requirements. Another one is your, oops, sorry, here, table 6.1. Table 6.1, these are ventilated requirements, but it can also have air conditioning air. So as on top of your air conditioning, this outdoor air must be introduced into your spaces. So table 6.1 specifies those spaces, even though they are air-conditioned spaces, most of them are air-conditioned spaces, they still need outdoor air requirements. Okay. Was I able to answer your question, Engineer Gerardo? Another question from Apple. Sir, what are other or most important local codes to remember in the design or calculation of mechanical ventilation in manufacturing plants like sardines factory? First, if you are doing, first you need to know your locality. So for me, I'm in Singapore, so my code is SS553. If you're in the Philippines, so your code is Philippine Mechanical Engineering Code. However, the code does not specify all things that you need to know. So you need to get other codes that are available. For example, in your area, manufacturing plant, I don't know if you are GMP. I don't know if there are other or clean room, because you're handling food. So there's a cleanliness factor there. So there are other codes that are specifying there. For us here in Singapore, we are using the British standard, so BS-RIA. So for us, it's BS-RIA. I'm not too sure in the Philippines. I think it's all in the ASHRAE standards. So ASHRAE standards in manufacturing plants, ASHRAE standards in air cleanliness, ASHRAE standards in laboratories and fume hoods. There you go. So depending on your locality, no, check your local codes first. That's first and foremost standard that you need to refer to whichever locality kayo. So for example, for me, if I'm working in Singapore, the person who will be signing my plans will also be in Singapore. So if your plant is there in the Philippines, the person who's signing your plans will be also from the Philippines and would most likely be referring to your local codes. So local codes first. If not, check ASHRAE. ASHRAE, if mechanical ventilation design, they have all the codes and all the values that you'll be needing. So thank you. I don't see any more questions. So if there's no more questions, I appreciate you guys for attending, and I appreciate you guys participating in our training. Again, this training will be available in Facebook. I will also be sending you the slides if you have registered, and I will also be sending out the certificates for those who have requested them. For our next training, our training will be next week, December 19, same time, 7:30, overview of duct design. So if there's nothing else, I say thank you and stay safe. Bye.
Thank you.